What's up, everybody? Welcome to Geology. Let's talk metamorphic rocks. Let's see if I can make this a little bigger. What we got? This chart right here, you may have seen if you're in my class. This is part of the open textbook that we use, the online free textbook. What we got is a chart that shows us as you go deeper within the Earth, what happens, and then specifically at those different depths, what happens as the rock gets hotter and hotter and hotter for various geological tectonic reasons, right? And then what we're talking about is basically in this realm right here, we've got what would be metamorphic rocks, because this is where you have enough heat and pressure to alter the minerals, but not so much that it melts it. When you get past this red line over here, you've entered the zone of melting off the rock. And if it melts, then we've gone over to the world of igneous once that rock cools off. No longer metamorphic. So it's kind of a fine balance. A tiny bit of heat and pressure might even be where you form sedimentary in this very tippy top corner. And then more and more heat and pressure will make these rocks. Now, the green dotted line here, you've got these rocks, and I put them in this order in your rock drawer: slate, phyllite, schist, and gneiss. There's parts of this lab that are harder than other ones. So I'm going to give some kind of heavy-handed hints here to help out. And once you figure out where we're at, those four are in that order to reflect what happens as we go through more and more and more heat and pressure with these rocks. That would be what we call, and you're going to have to define this here in a minute, it's regional metamorphism. That's when we're talking like mountains that go banging into each other, or when continents really go banging into each other and develop mountains down in the roots of that. Again, where there's enough heat and pressure to alter but not melt the minerals. Up here towards the top where this one says Hornfels, that could be, say, we're getting high heats, but not really that much pressure. What that's going to be is something called, generally, contact metamorphism, which is when there's a nearby source of a significant amount of heat, like a nearby lava. So if, let's say, picture what we talked about with igneous, magma within the crust working its way up. What about the rock that it contacts, touches, and doesn't melt? What gets hot but doesn't necessarily build up like tectonic pressures? That would be living up here towards the top. The bottom left here, and I guess I'll do the blue line first. Subduction metamorphism is kind of the rarest. It's the hardest to find because what you need there is in a subduction zone tectonically when rock is being pulled down into the earth. In other words, it's going down so fast that it gets down to these higher. Sorry.
Elijah here to the main office.
Sorry. It goes down to these significant depths, but doesn't necessarily get hot because it's going down so fast. They're fairly rare to find because they got to get down there and then somehow get back up to the earth for us humans to find them. Hint, hint, they're not in the lab. And then the very bottom left here would be, well, that doesn't really happen. You can't get that deep within the earth without also increasing the temperature. All right. So what are we going to do here? What I've got, a couple questions there. I've got a chart that's going to take you through the basic types of rocks. I didn't even do all of these. And then your usual, what we've been doing in the lab by rock number in your rock drawer, right? What I'm also going to put in is another one of the professor's online labs. And I've been kind of basing a lot of my stuff on her work. But I'm going to straight up put this one in there because there's like hints that I think are going to be pretty helpful. Because again, this is hard. I always, igneous is the easiest one to do. It might seem intimidating at the beginning, but it's like darker light, coarser fine, job done. Here, there's a lot more paying attention to detail, doing descriptions. I mean, look how different all of these look, right? So I'm thinking that if you take the samples that are in your rock drawer and then maybe kind of match them up, even if they don't look identical, you'll have to do a little thinking, but you'll figure it out. Matching up with these descriptions right here that can help. You're not doing this lab. Don't worry about any of the stuff up above or any of the stuff way down below. I'm just saying use this lab. Maybe I'll even reduce the pages here. That's a good idea. I'll do that. Sorry, thinking on my feet. I'll reduce it down to just these with the rock samples for her online lab with those little descriptions. Then you go to our rock drawer and use your head and say, okay, that one kind of looks like that, and therefore this little blurb is going to help me. Sound good? The descriptions here are probably what I'm most interested in looking at. So don't just, like, if you just say, it's pink, then maybe I'm going to say you're not working too hard on this. if you give me a good description of what it looks like, which I understand can be challenging, but use both what is in that lab that's posted, and you can look at these comments here. Because this is where, especially considering that we're saving our minerals lab for last, this is where maybe, I mean, read this here. Are you going to like look at one of the pictures and say, oh, I see foliation surfaces shiny from microscopic microcrystals? Nobody's ever said that the first time that they pick up a piece of phyllite, right? So you're going to like cheat a tiny bit by using this table, using your observations, using what you see in the picture, and using the other lab to help you connect all the dots. Because otherwise, I think this is pretty difficult. That hopefully is enough to make it a touch easier. All right. Sound good, everybody? Email if you have any questions. Best of luck.